Hi guys, and welcome to another video in a series of HSC Chemistry production of materials. Today I'm going to look at oxidation states and how we can identify oxidants and reductants in redox couples. The references that we're specifically looking at here relate to accounting for changes in the oxidation state, so that's a term we need to be familiar with. In terms of loss or gain of electrons, so we're looking at reduction or oxidation. And then we need to describe and explain galvanic cells in terms of oxidation reduction reactions. Now the second one we'll look at in a little bit more detail when we're actually setting these up in the classroom. But today we want to focus a little bit on oxidation state. So have a look at the two equations that are on the slide at the moment. In an ordinary dry cell battery, we have a zinc electrode, and the zinc electrode is losing electrons. So this is oxidation. Zinc is going from its elemental state, which it has a balance of charge, to a 2+ ion. And it does that by losing 2 electrons. I've talked to you briefly before about the little number plane, and the number plane is quite useful in giving us a little bit of an idea. So the zinc has gone from 0 to 2+. So it's moved in the ox direction. When we look at the second of these reactions, we can see that there's an electron on the reactant side. Now it's kind of difficult to tell just by looking at this, but actually what we need to do is look at the manganese. Manganese dioxide, if oxygen is -2, then 2 of those is -4, so therefore the manganese must be +4 on the left-hand side of this equation. But we also know that hydroxide is -1, and therefore 3 of them is -3, and so the manganese is now +3 in order for this to be balanced. So if you have a look at the number plane, and I'll just extend that a little bit up here, the manganese has actually gone from +4 to +3. So it's actually gone in the opposite direction along our number plane. And this direction indicates reduction. So it's the manganese species that's been reduced, and it's the zinc that's been oxidized. So when we look at our question, the species that's being oxidized, this is the species that is losing electrons, is the zinc, and the one that's being reduced is the manganese. Often these equations are very complex, and so it's very difficult for us to identify what's going on just by looking at them. The first of these equations is reasonably straightforward, zinc becoming zinc ions. You probably pick up very quickly. But the second equation is much more complex, and it's much more difficult to try and identify just straight off what is actually happening. The concept of oxidation states, or also referred to as oxidation number, is a way of helping us to identify what's actually going on in a redox couple. So the oxidation state or oxidation number is an indicator of the degree of oxidation. Just come back to blue for a second. The degree of oxidation of an atom or ion in a chemical compound. And there are a couple of rules that we need to follow in order for us to determine oxidation states of atoms. There's a nice little picture here of vanadium ions in 4 different oxidation states. Of course, not all oxidation states correspond to different colors, but some do. So the first rule is that elements in the elemental state have an oxidation state of 0. We've looked at this before. So here is silver solid. It has an oxidation state of 0. And so does copper, and so does manganese. Provided they are in their elemental states, the assumption that we make is always that they're 0. Likewise, if a molecule contains only one element, then it likewise has an oxidation state of 0. So this covers things like hydrogen gas, oxygen gas, nitrogen gas, chlorine gas, and so on. On their own, as the elemental state, they have an oxidation number or oxidation state equal to 0. The second rule is that for monatomic ions, the oxidation state equals the charge on the ion. So an Mg2+ ion has a +2 oxidation state. A Cu3+ would have a 3+ oxidation state. A Cl-, a -1, and so on. The trick comes when we start looking at polyatomic species, where there is a number of different atoms present in the polyatomic ion, and we have to kind of work things out overall. So when we have polyatomic species, we have to make sure that the sum of the oxidation states, in all of the species equals the charge. In ammonia, the overall charge is 0. It's a compound, not an ion. So therefore, the sum of the nitrogen and the 3 hydrogens must equal 0. In ammonium, it's a 1+ ion. So therefore, the sum of the oxidation states of the nitrogen and the 4 hydrogens must actually equal to +1. Likewise for the nitrate ion and for the dichromate ion. Now what this means is we need to start looking at how each of these is represented and to therefore calculate individual components. So if, for example, we look at the nitrate ion, we know that the total is going to have to equal -1. But how do we assign values to the nitrogen and the oxygen? Well, that's going to come up in one of our other rules. Oxygen is almost always -2 in compounds. We did look at the exception to that, which was the peroxide ion, the H2O2, where oxygen actually takes a -1 charge. But almost always you can assume oxygen is going to be -2. Fluorine is -1, and hydrogen is almost always +1, and then there are exceptions. So if we go back to our nitrate ion, which was -1, and if we assume that the oxygen is -2, then we have 3 of those for -6. Because we want an overall charge of -1, then the nitrogen must be +5. +5 minus 6 is -1. So here's a question to practice. Determine the oxidation state of the chromium in the dichromate ion. So we want to know what this is. Well, the assumption that we're going to make is that the oxygen is a -2. We've got 7 of those, so we're going to end up with 7 times -2 is -14. But overall, we want a 2- charge, so therefore we need to get 12 pluses out of our chromium. And so therefore, if there are 2 of them, then each individual one must be +6. So this requires a mathematical approach for us to work through these stages. An alternative is to just solve it as an algebraic expression or an equation. So if the oxidation state of the chromium is X, then 2 times X, which is the chromium, plus -2 times 7, which is the oxygen, must be equivalent to the overall charge, which is -2. 2x then, -14 equals 2, 2x equals 12, and x equals 6, exactly as we did over here. With many of these problems, there's going to be multiple solutions. You need to just work out which way is going to work best for you so that you can consistently get the correct response. So why is this important? The importance of oxidation state helps us to determine whether or not a species has undergone oxidation or reduction, and that's what it's all about. So if we determine the oxidation state of the metal atoms on either side of the equations here, then because copper is in its elemental state as a solid, it has an oxidation state of 0. The copper ion is +2. The silver ion is +1, and silver solid in its elemental state is 0. As a consequence of that, again, if we think of our number plane, one of these is going from 0 to 2, and one of them is going from 1 to 0. One is moving along the oxidation region or direction of our number plane, and the other one is moving along the reduction. So it's the silver that's reduced, gaining electrons, and it's the copper that's oxidized, losing those electrons. So the thing with the number plane is the number plane really just tells us what's actually going on in terms of change. So oxidation leads to an increase in the oxidation state. That is, the numbers get bigger, even if they're -1 going to 0. As long as we're moving in the positive direction, increasing the number, that's oxidation. Reduction is the opposite direction. So 3 back to 2, back to 1, and so forth. Decreasing the oxidation state is reduction. So one more question for you here. Determine whether the following are redox reactions. Well, how do we do that? What we do is we have a look to see if the states have changed at all. So for mercury in its elemental state, it would be 0. For oxygen in its elemental state, it would be 0. And then as a compound, the oxygen is -2, and therefore the mercury must be +2. So this is changes in oxidation state, and hence we have a redox reaction. In the second one, oxygen is -2, so therefore the copper must be +2. Hydrogen is in its elemental state as a diatomic molecule, so it's 0. The copper in this case goes to its elemental state as a solid, so it goes back to 0. And the oxygen is -2, but the hydrogen therefore must be +1. And so because again we've had a change in hydrogen and a change in copper, this is an example of a redox reaction. In the final one, if we look at the oxygen being a -2, 4 of those is -8, with an overall charge of -2 means we have 6 altogether. So the chromium in this case is a 6+, and hydrogen over here is a +1 because it's an ion. This one we worked out before, so if oxygen is -2, 7 of those -2s will be -14. We need -2, so we need +12 altogether. Dividing 12 by 2, we get +6 for the chromium. The hydrogen will remain +1 and the oxygen will be -2. In this case, there's been no change in the oxidation state for the chromium, the oxygen, or the hydrogen, and hence this is not a redox reaction. Just a little bit of terminology to finish off, and I know this has been a longer video than usual, so let's just wrap things up now. 2 terms that may come up in your questions or in your readings are the terms oxidant and reductant. The species which undergoes oxidation is itself a reductant. That is because if it's undergoing oxidation, if it's losing electrons, it is able to donate them to something else. That is, force some other species to gain the electrons. So it is causing reduction. Reactive metals such as potassium, sodium, lithium, and so on are very strong reductants. They are very readily lose their electrons, and therefore they are readily oxidized, able to cause reduction in other species. Cations of unreactive metals such as gold, silver, and copper easily undergo reduction and are therefore strong oxidants. So the reverse is also true. Anything that readily undergoes reduction can act as a strong oxidant. That is, it can pull electrons away from other species. So these are just 2 terms you may see. So as a final question then for this particular video, can you identify the reductant and the oxidant in the following redox equations? Well, again, it's useful for us to use oxidation numbers. So elemental states are always 0. In this case, the chlorine is a -1 and the sodium is a +1. Our periodic table will tell us this. So on our number plane, sodium has gone from 0 to +1, so it's been oxidized, so therefore it is the reductant. Chlorine has gone from 0 to -1, so it's gone in the reduction direction, so it is the oxidant. Sounds back to front, but that's how it works. And this one, because we've already hit the 15-minute mark, I'm going to leave for you. Ask me tomorrow. Thanks for watching.